All right, let's jump right in. Today we're tackling a topic that's at the heart of all chemistry, but can be a little tricky when it shows up on an exam: the states of matter. So if you're getting ready for the GPAT, or hey, even if you just need a good refresher, you are in exactly the right place. We're going to break this all down so it's easy to get and, even better, easy to remember.
So, let's start with a big question. What really makes a solid? Or a liquid? It sounds so basic, right? But the answer is actually this awesome story about a constant tug-of-war that's happening between billions and billions of molecules. You've got energy trying to push them all apart, and these sticky forces trying to pull them all together. And if you understand that battle, you've pretty much mastered this whole subject.
Okay, so first things first, let's talk about the big three, the states of matter that we actually see and deal with every single day. Think about a solid like a perfectly disciplined army, all standing in a neat formation. Every single atom or molecule is basically locked into place, held super tight by these powerful forces. That's exactly why a chunk of ice, for example, is going to hold its shape and its volume no matter what you do with it.
Now, what about liquids? Well, things are a little more chilled out here. The molecules have some wiggle room. Yeah, they're still packed in pretty close, but they can slide and just kind of flow right past each other. And that, of course, is why a liquid will take the shape of whatever you pour it into, but its volume stays the same. And then you've got gases. Oh man, these are the total rebels of the molecular world. They're just buzzing with so much energy that they've completely broken free from each other. They'll just zip around like crazy and expand to fill any container you put them in. Doesn't matter how big it is.
So, here's the bottom line, the quick and dirty summary you need to remember. Solids, they're fixed, locked in. Liquids, they flow, but their volume is fixed. And gases, total free-for-all. They'll take any shape and any volume. Got it? Good.
Okay, so we've nailed the what. But now for the why, which honestly is where it gets super interesting. What is this invisible glue holding everything together? Well, it all comes down to something called intermolecular forces.
Turns out, this molecular glue comes in a couple of different strengths. You've got the van der Waals forces, which can be pretty weak, like London dispersion forces, or a bit stronger, like dipole-dipole interactions. And then you have the big one, the undisputed heavyweight champ of them all, hydrogen bonding.
And this is a great little chart because it connects all the dots. Look at methane on one end. It's only held together by those weak London forces, so its boiling point is incredibly low. But then you look at water, and that's a whole different ballgame. It has those super strong hydrogen bonds, which act like molecular superglue. You have to pump in a ton of energy to break them apart. And that's why water's boiling point is so high, and it's a huge reason why life on Earth is even possible.
All right, let's switch gears back to gases for a sec. We all had to memorize the ideal gas law, right? PV equals nRT. And it's a great rule of thumb, but here's the thing. In the real world, it's a little too simple. It's kind of like a cartoon map of the world. It gets the big picture right, but all the important details are missing, especially when things get intense, like under high pressure.
So, where does it go wrong? Well, the ideal gas law makes two pretty huge and kind of false assumptions. First, it pretends gas molecules are just these tiny, zero-volume dots. And second, it pretends they don't attract each other at all. But in reality, molecules take up space and they're always pulling on each other. And when you really start to squeeze them together or cool them way down, those little details suddenly become a huge deal.
So how do we fix it? Enter the van der Waals equation. It looks a little intimidating, I know, but it's brilliant. It basically takes the ideal gas law and gives it a reality check with these two clever little correction factors, A and B, to account for how real gases actually work.
Let's break it down. The A factor, that's all about attraction. Picture a molecule flying towards the wall of a container. In a real gas, all its little buddies are pulling it back, right? So it doesn't hit the wall with as much force as it would have. This A term just corrects for that. It adds that lost pressure back into the equation.
Then you've got the B factor. This one's even simpler. It's all about size. Molecules aren't invisible dots, you know? They're real things that take up real space. So the B term just subtracts the volume of the molecules themselves from the total volume of the container. That gives you the actual space they have left to zip around in.
Okay, so now that we get how these real-world forces work, we can actually start to manipulate them. And this is where it gets really fun, because we can do things like turn a gas into a liquid. It's a process called liquefaction, and it's an incredibly powerful tool.
It's basically a classic 1-2 punch. First, you have to cool the gas way down. that slows down all those hyperactive molecules. Then you squeeze it hard. You crank up the pressure to force them all closer together. And once they're slow enough and close enough, those sticky intermolecular forces we talked about can finally take over, and boom, you've got a liquid.
But, and this is a huge but, something you absolutely have to know for your exams, there's a catch. Every single gas has this point of no return. It's called its critical temperature. And if you go even 1 degree above it, those molecules are just moving too fast. You can apply all the pressure in the universe and it will not turn into a liquid. Game over.
And this chart really shows you just how different that point of no return is for different gases. You've got hydrogen, which you have to get insanely cold, like minus 240 Celsius. But then, check out carbon dioxide. Its critical temperature is about 31 degrees Celsius. That's just a little warmer than room temperature, which means you can turn CO2 gas into a liquid just by squeezing it hard enough. It's pretty wild when you think about it. It's how they get the caffeine out of your coffee beans.
Okay, we have covered a ton. So, you ready to see if it all stuck? Let's do a couple of quick-fire questions, GPAT-style, to lock it all in. Question 1. In a nutshell, what's the big deal with the van der Waals equation? What does it fix that the ideal gas law gets wrong?
Bingo. It just brings things back to reality. It reminds us that molecules aren't just dots. They have volume, and they have attraction for each other. Simple as that.
All right, next question. Back to our friend water. What's the secret behind its surprisingly high boiling point? That's it. It is all about that hydrogen bonding. It creates this incredibly strong molecular web that's just really, really tough to break out of. You have to pump in a ton of extra heat energy to finally do it. Okay, last one. And this one's a bit of a brain teaser. We know we can turn a gas into a liquid. But what happens if you take a substance and push it beyond its critical temperature and pressure? You don't get a liquid, but you don't really have a gas either. You enter this weird, amazing fourth state of matter where the line between liquid and gas just disappears. It's called a supercritical fluid, and honestly, it's some next-level stuff with some truly mind-blowing uses. But we'll have to save that deep dive for another time. For now, I hope this all clicked. Keep asking those questions and keep exploring.